So I'm going to talk about turbulent dynamos, but there should be really zero overlap with the previous talk on turbulent dynamos for reasons I'll explain. For motivation, because I'm a paper and pencil kind of guy, I don't have movies to show. So I'm starting out with a picture of a nearby star in X-rays with the magnetic field lines drawn in. I should mention two things are obvious from this first slide. First of all, my former graduate student, Amir Jafari, did a lot of the work that I'll be talking about. And the other thing is that I wrote the slides last month and forgot to change the month. So what is the problem that I'll be talking about? I'll be talking about the large-scale dynamo problem, which is to say, how do magnetic fields get produced on scales much larger than the Eddy scale, not part of the turbulent cascade, but on the system scale? It's the large-scale dynamo problem. It's a general process in the universe, takes place in stars, galaxies, accretion disks, planets. And the computational simulations of this process have been challenging and often disappointing. I'm not going to say very much about them, but it's because the results are heterogeneous, and the experimental tests of this process have in particular been difficult to compare directly to what we see in nature. So first of all, my point is that the production of large-scale magnetic fields are an example of self-organization, a kind of inverse cascade, but extending well beyond the scale of the turbulence, in the presence of rotation and or shear. Here's another example, not a magnetic one, of a self-organized large-scale structure impacting the state of Alabama. Everyone in Alabama survived recently, yes. So there's a cartoon which people always draw to talk about this, and I've just copied it, one particular copy out of a textbook, a review article. This is a ball representing a star. There's a poloidal field. Here are the lines drawn in. The star is differentially rotating. It winds up the field lines. They become extremely wound up. If we consider just the toroidal part of the field, and now here magic occurs. The underlying velocity field takes these field lines and makes them into spirals. They reconnect, and because of the gradient and the strength of the spirals and the strength of the field, we are left with a residual piece which adds to or could subtract from the original poloidal field. So this kind of process is called an alpha-omega dynamo. The stretching parts are called, that's the omega part, the shear part, and this part is the alpha part. Now I referred to this as magic because in fact you can't do this. The point which wasn't realized for a good long time. But let me talk about the equations here. This is a mean field theory that I'm going to use. We're talking about a highly conducting fluid, so the Lorentz force vanishes in the frame of the fluid. We have a simple form of the induction equation, and I'm going to ignore the resistive terms. They're non-zero. The fact that they're non-zero is important for reconnection, but they do not affect the dynamics, and we can ignore them in the sense that Greg Eink urged in his talk. So we construct a mean field dynamo theory out of this in the usual way. Several people have talked about various methods of coarse graining. I'm just going to do a very simple process in which there's a range of scales that describe the turbulence, and there are a range of larger scales that are everything else. If we do that, we write the induction equation in this way, where capital B is now the large-scale field. The large-scale field is moved around by the large-scale velocity field. It is stretched by the large-scale velocity field. And then there's this turbulent piece, this coarse-grained electric field that arises from eddy scale motions and magnetic fields. How do we calculate that? I mean, offhand, that could be zero. So we can estimate the correlations involved. I'm going to follow Pouquet on this. What we do is we take the time derivative and we balance that with a decorrelation process with some characteristic time, tau sub c, which is the eddy turnover time, basically. And then we just say, well, that means that the mean value is sort of a Taylor expansion around the state where it's 0. We can just take the time derivative of the velocity, cross it with the magnetic field, or the velocity field cross the time derivative of the magnetic field, multiply by the correlation time. This is all very standard stuff. We leave out a few steps, and we get that the electromotive force is a current helicity tensor, which I'll define in a second, minus a kinetic helicity tensor, times the magnetic field, and times the coherence time. And there are a few other things which pop up. You can get the magnetic field can be drifting through the fluid, so that takes the form of a velocity times the large-scale field. And there are dissipative terms which correspond to the turbulence mixing the magnetic field lines. The pseudoscalar current helicity, little j dot little b, the curling of the eddy scale magnetic field. It's related to the magnetic helicity, depending on your gauge, by a constant. I'll come back to that in a second. The point is that j dot b is an expression of a conserved quantity. It's not something you can just decide is non-zero. It's not something that's produced by the local dynamics. Normally, when people talk about mean field dynamo theory, they look at the kinetic helicity tensor instead, the kinetic helicity v dot vorticity. But this is imposed by the environment. It's not a conserved quantity, and in general, it's actually ignorable. So I'm not going to talk about that much, except to say a little bit, in a little while I'll say why it's ignorable. Oh, I mistimed those things. Okay, so what is the current helicity? What is the current helicity tensor? This thing is a matrix which expresses the anisotropy of the eddies. It's basically the product of two wave vector unit vectors in Fourier space. So the trace of this matrix is 1. Where it's large, that means the eddies are flattened in that direction. Where it's small, that means that the eddies are extended in that direction. And you can show analytically that if you know, if you know the current helicity, then this is the current helicity tensor. You multiply by the magnetic field to get the electromotive force. Oh, and the correlation time. This thing, J dot B, is related to the fluctuating magnetic potential times the fluctuating magnetic field times the k squared, where k is the wave vector of the eddies. If you average on the scale of the eddies, this turns out to be, for the Coulomb potential, really just a constant. Okay. Why is the magnetic helicity interesting? Some of you know about this quantity a lot. Some of you may not know about it at all. But it's an example of a Chern-Simons symmetry. And it's the same Simons, amusingly enough. In quantum field theories, when you have conserved topological quantities, they can sometimes be expressed as A wedge F, where F is the field tensor and A is the potential. This, as far as I know, is the only classical example of where it's important. In MHD, the Chern-Simons symmetry for the field A dot B is a topological quantity, an expression of how much coiling and interlocking there is of field loops. So it's a global quantity. It's sensitive to gauge as a local value. But if you pick a gauge that is particularly nice, like the Coulomb gauge, then the current helicity, which is not gauge dependent, is just proportional to it. Now, the eddy scale quantity is not the whole thing. So it is not conserved, and you can write down the conservation law for it. It's this thing, where this is the part that's not conserved. This corresponds to the transfer of magnetic helicity between scales. In other words, this is the term that describes all those spirals being reconnected and giving you fresh colloidal field. It's the mathematical version of that step in the cartoon. And the reason why that step is magic is because if all we have is this term and this term, then all you can do is trade magnetic helicity off between scales. And what we now know is that if you do that, the system pushes back. It's like taking a rope and trying to bend it into a spiral without moving the endpoints. In fact, it's exactly like that. It's the same topological problem. So this thing is what's important. It represents the ability of the system to move eddy scale magnetic helicity around on large scales.
You used the word reconnection. Is that really the right word?
Yeah, because I'm going from drawing field lines in one configuration to averaging them out and drawing them in another. I'm just assuming that that's an efficient process here.
Ethan, sorry, what is your little b here?
Oh, that's the fluctuating magnetic field.
I see. So are you explaining it as like big B times 1 plus little b, or is it?
No, it's big B and little b.
So little b is also a physical unit.
Yes. These things are both measurable physical units, but they don't talk to each other directly. So the point is, what you need to make the dynamo process run is to make this term non-zero. And that makes the magic step in the alpha omega dynamo doable. Having done that, you have to then transfer the magnetic helicity between scales rather than let it pile up. And there's a characteristic time scale for that to happen, which, if the field is strong, can be like an eddy turnover time, but if the field is weak, it's going to be slower. And when it's slow, then you have to worry that you're not in a stationary state and magnetic helicity is increasing or decreasing in a substantial way. So what is the magnetic helicity flux, and can we talk about it in an intelligent way? Okay, this is the definition for the magnetic helicity flux in a shearing system, assuming the Coulomb gauge. And this is the fluctuating electrostatic potential. This is the shear tensor. So this has two terms, and this one corresponds to the shear rolling up field lines that are embedded in the fluid. And this corresponds to a dynamic process in which the magnetic helicity goes from one eddy to another. And we can estimate it just by the same process that we use to estimate V cross B, that is to say, balancing growth with turbulent decorrelation. It is a more complicated process because in order for this to have a direction, there has to be some large-scale symmetry breaking. So there has to be some dependence on large-scale shear and rotation, or shear or rotation. And because this is a triple product in the fields, in order to get an estimate, you need to take a time derivative to get to the coupled terms and get a fourth order quantity. So that means you're actually having to take two time derivatives. And the whole problem is extremely messy and would not be edifying if I showed you the answer. But fortunately, we can do a dimensional estimate, and the arguments really follow from that. It's going to be like v squared times b squared. I said there were two time derivatives, so there's two correlation times there. Either the shear or the rotation can drive this. And there are some eddy shape factors, which are various expressions of those R's I talked about. And they're going to be very important when the star is when you have a rapidly rotating star and highly anisotropic turbulence. Convection by itself is a little bit anisotropic anyhow, because it knows the difference between up and down and right and left. So let me move right along, because I wasn't keeping track of time. You can ask how long it takes for this flow to produce a current helicity term, which will dominate over the kinetic helicity term, and it's one eddy turnover time, which is to say the shortest time that you can talk about in a mean field theory. And therefore, the kinetic helicity is never important in the dynamo process. Okay, let's just skip over this. This is a mess. What you can say, though, briefly, is that because the magnetic helicity flux doesn't depend on the strength of the large-scale field, the electromotive force goes inversely with the strength of the field. And that means that the rate at which the dynamo goes starts out very fast and slows down, as long as you're efficiently transferring magnetic helicity between scales. So if you have a turbulent dissipation, it will balance it at some point as the field becomes strong, even though the rate of turbulent dissipation will remain constant. So let me skip over these caveats, which are all about a more... if you balance all this together, and whether you in a box, or you can make the box the size of a pressure scale height if you're talking about a real star, you get an estimate for a slow rotator of the saturated strength, which goes as the geometric mean of the shear and the rotation rate. So if the relative shear, for example, is a function of the Rossby number, you're going to get something which is a bit steeper than the rotation rate as a dependence. In the rapidly rotating limit, you get something that depends only on the relative shear, which we just learned goes to a constant value. Let's see. I like this graph. Here we go. You can get an estimate of the internal magnetic field of stars by looking at Zeeman splitting of infrared lines from cool stars. And that's presumably giving you a measure of the star spots on the surface of the star, the magnetic field strength in those, which is a measure of the buried magnetic toroidal field. And so if you plot those against Rossby number, you have here rapidly rotating things, and there's a plateau, and slowly rotating things, and you have this line which is slightly steeper than being dependent just on 1 power of the rotation rate. So the stupidest model gives you actually a pretty good answer. And we're not going to worry about the subtleties, and I'm not going to take the time to diss numerical simulations. I will just say you need to conserve magnetic helicity on eddy scales over the dynamo time scale in order to do this problem. And that can be challenging. So this is a great model. It gives you a scaling for stellar magnetic fields for no work at all. It poses a challenge for the numerics. And by the way, it works great for galaxies. And it's totally different from the usual mean field dynamo models, which is good because they violate physical law. Sorry.
Great. Let's thank Ethan for that. We have time for just a couple of questions. See.
Me? Oh, thanks. Isa,
Comment on the interaction between the mean field dynamo and the small scale turbulent dynamo.
Right. So in this treatment, I have assumed that the small scale dynamo has run to equipartition on this large eddy scale. And in practice, if you're talking about things like, the formation of galactic disks, that's going to take a little while. So this process won't start the moment galaxies form. It'll wait until the small scale dynamo has gone largely to completion before it can start. But normally we're dealing with systems like stars where the small scale dynamo has already done its thing.
I'll ask something similar to what I asked Xiao. Like in all of these dynamo talks, I'm always missing the role of the compressibility, which will, of course, work with the flux freezing in an interesting way to compress and amplify magnetic fields. So when you have shocks, how does that play into this picture?
So compression is sort of an unsatisfying way to amplify magnetic fields because it doesn't change the flux through a fluid element. It just changes the local field strength by compressing the matter. And that can be interesting in its own right, but a successful large-scale dynamo requires something that grows when the system is static in that sense.
But all of these dynamo studies, especially the analytic ones, of course, they're working more or less with incompressible equations.
So as long as you're dealing with fluid motions that are relatively slow, that's not a problem. If you want to worry about things like, how does the magnetic field of a supernova remnant get going, then yeah, that's inadequate. You really do want to worry about the compressive shock and the dynamics that follow behind it in order to discuss dynamo processes. And I'm not going to say anything about that.
So this seems to actually make pretty definite predictions for the galactic dynamo and how it evolves.
Yes.
Right? So, what the magnetic field strength should be as a function of redshift for galaxies and also it's the topology of the galactic fields.
So there's part of the answer, part of my answer to that is pretty definite and part of it is unfortunately a little vague. And I'll tell you the definite part first. The definite part is that if you consider a galaxy that's newly formed, let's say you've waited several eddy turnover times or maybe 20 or so, and the small scale dynamo has done its thing, and then there's this magnetic helicity current that's aligned with the axis of rotation of the galaxy. It'll drive annular magnetic domains, and it will do so very quickly. So the limit on the speed there is set basically by the fact that the small scale helicity will tend to saturate. And so the process won't be maximally effective, but it will still take only a few rotation times to basically run through. And it will use as a seed for the large scale field the long wavelength tail that you get from the turbulent process. So all of this goes pretty quickly. The part I don't know the answer to is, how do you go from those annular magnetic domains to the large-scale fields we see in galaxies today, which seem to have few reversals as you go outward in radius? I'm not sure how that happens naturally, and I'm not sure whether it involves radial diffusion within the disk or somehow the thick disk or the halo are intimately involved in this, but something extra is going on.
Galaxies aren't isolated systems. They're blowing wind. There's matter coming in, right? And that's both affected by the field lines and interacting with them. So how that all goes is not unclear.
Right. I mean, it's easy to talk about a toy field in a box, but that's not where we are.
Well, that's a great note to think about for the discussion later today, but I think we have to wrap up and move to the next talk. So let's thank Ethan again.
Thank you very much. Yeah, I'm very glad to be here. So I'd like to thank the organizers for the invitation. So I'm glad to be here for a number of reasons. So I started out with a PhD attempt with Rashid Sunyaev working on accretion. And that's actually also where I saw David for the first time. So you gave it was somewhere between the first year and second release of WMAP data at that time. So now basically, then I switched fields and started over the last years. Basically, I've mostly worked on active fluids, and now we're kind of back. So the system I'll be talking about in my talk today, they're mostly of this type or are motivated by this type. So this is a bacterial suspension. And here it's confined basically in a microfluidic device. So the scale here is roughly 50 microns of one of these little basins. And so we basically developed or started to look into very simple models for these type of systems. And then what we've done lately, and this is something my PhD student Rohit will talk or speak in the last talk today about, and it's basically just described in a paper that we put on the archive last night, and we hope to get some feedback on that actually, is that we can take the same equations that we basically invented to describe these type of systems. Or I will actually say later on that we didn't really invent them, so we thought we invented them, but then you look into the literature and you find similar equations in other fields. And so what I've shown here is basically simulation of the same equation just in two different settings. And so in a sense, I hope that plays into the theme of the workshop. Of course, trying to come up with a very general equation that just keeps this generic aspect come at the expense of detail. So what I describe here won't capture details of specific systems, but I hope basically it is useful in some sense so that it shows what the similarities are, maybe on some very, very basic level. Okay, so because I think most here are not from my community, I just want to give you an idea how we arrived at these type of equations. And so what we're mostly interested in is pattern formation in all sorts of systems. So in embryogenesis, also on soft materials, and this is basically has been discussed here by our collaborators, Nikta's PhD students, Jing Hui, and also my student Pearson yesterday, I think. And so these are basically elastic system, and this is living on a membrane. And then we're also interested basically in complex fluids. And what I will talk about today is mostly this lower left corner, but the type of equations that we use to describe these are higher order PDEs, and they're very natural in these systems. Good. Okay, so the results I'll present are the product of a collaboration with many different brilliant experimentalists and PhD students. So I highlighted here a number of them. So the experiments I'll show, they're mostly due to Hugo Wieland and Knut Drescher, who were PhD students in Ray Goldstein's lab when I was a postdoc there. And the theoretical results I'll present are due to Jonas Slomka, who's now at ETH, and Rohit. And then there were a number of people who helped us at various stages. So I would like to highlight in particular the Daedalus team. So we've seen some pieces today already of the code, and I'll show nice movies again, obviously that are based on their code. And yeah, and also a number of instructors in our math department who helped with details, and I will point out basically where their contributions lie. Good. So I'll spend about 10 minutes or so to motivate where these equations come from and why we basically boiled things down to a very basic model. And then I will talk about the structure of the equation. So that's the bulk of the talk. And then I'll talk about exact solutions between 2D and 3D, and some basically surprising symmetry breaking mechanism, and also about how this relates to triads in classical Navier-Stokes. And then I will close with a very short outlook or intro to Rohit's talk. Good. So what we've seen already here in this workshop is that there are various active matter systems that spontaneously form scales. So, through different mechanisms. So here are three examples. So these are ATP-driven microtubules that essentially walk on a glass surface, and they form these vortical structures. This is from Sonimer's active liquid crystal system. So here the typical scale, in a sense, is a distance between defects, which is, if you look at the distribution of distances, is very narrowly peaked. This is another example. These are sea urchin sperm cells, and they are at sufficiently high concentrations, basically close to a glass slide. They spontaneously assemble into these almost hexagonal or triangular lattices. And if you zoom into these little, lattice sites, so then you find that there is a little vortex sitting with 50 to 100 cells or so. So these are examples where basically these systems spontaneously form scales, and this is something I will assume later on and just put it into the model. So the system we've been working with mostly are bacterial suspensions. So what you can see here is a typical movie of a bacterial suspension. So the experiment here is performed in a microfluidic channel. The channel is about 100 microns high and essentially infinite in the other 2 dimensions. And the objects that are swimming there are Bacillus subtilis bacteria. So they are little rods that can propel themselves, and typical swimming speeds are of the order of 10 to 20 micrometers per second. And if they are very high concentration, then they generate these type of flow fields. So this is a movie taken in the center of the channel. And it looks kind of turbulent, but there's a difference that you can see immediately. So there is also this typical scale somehow. So, and that length scale actually turns out to be of the order of 50 microns, and it has also been found in experiment by other groups. And the typical lifetime in bulk is of the order of a few seconds. So that's something you can vary with oxygen concentration. Good. So just to show you that there exists this length scale. So this is another experiment by Igor Arnzen, which essentially studies a similar system. So what they were able to do is to increase the concentration of bacteria gradually by basically running a current through a small platinum wire so that you change the concentration or ion concentration and can condense bacteria in the center. So they found basically 2 striking results. So one is, as you increase the concentration, so then if you look at the blue curve, you see that the mean swimming speed increases, so by a factor of 5 or so. So it is a sign basically that bacteria can collectively achieve larger swimming speeds or expansion velocities. The other thing that they found is that if you look at the green curve, that the correlation length in that basically system tails off. So if you add or basically approach a constant value, so if you're at roughly 0.3 here in the units, so you basically hit a typical correlation length, which is also basically in the range here of say 35 micrometers, and then basically that remains constant. So this is just another example that you have these emergent length scales, and as I said already, this is something I'll put into the model later on. So one thing you can ask now, if there's an intrinsic length scale, so can you use that length scale to actually control turbulence in these systems? And one way of controlling it is to build confinement that matches its length scale. So here you have a droplet, and this droplet has a diameter of 50 microns, which exactly matches this intrinsic length scale. And now what you can see, you get these very stable vortices that essentially live for minutes or so for as long as there is enough food. One thing that's worth pointing out, so this is the same movie, it's just thresholded here to show the orientational order, so that you have this spiral structure. So it looks as if basically there's a bulk motion basically that goes in basically clockwise direction, whereas the boundary layer goes in counterclockwise direction. And this is indeed the case. So you have essentially a monolayer on the boundary, and that creates a very strong backflow. And then the guys in the center, they still point in the same direction and swim also, or try to swim in the same direction as these in the boundary, but they're not fast enough to overcome the collective backflow. So this just shows that in these systems also basically boundary conditions play an important role. And then what we did is we played a little bit with these systems. So if you have a single basically droplet, you can combine them into a lattice, for example, and then try to control collective behavior. So what I've colored here, that's the same movie, is the angular momentum in each of these little wells. And what you can see here is that the system spontaneously arranges into a state of antiferromagnetic order. And this is what happens if these gaps here, or these, interaction sites are sufficiently small. If you make them a little bit larger, you can cause a transition to ferromagnetic order, where they all go in the same direction. And just to give you an idea, basically what the reason is, so if you have very narrow basically connections, then the cells essentially cannot swim through. So you have basically a circulation that goes along the boundary in this direction, the bulk circulation. That's what the eye sees, basically appears to go in the opposite direction due to the backflow. And then if you want to minimize viscous friction across the intersection, so you want to go in the same direction here, which means that the bulk flow goes in the opposite direction, which gives you this antiferromagnetic pattern. If you basically make the gap large enough, then bacteria can swim through. So what they try to do is also swim close to boundaries. So they follow through here, so you get a continuous current here. You also want a continuous current here, so then that means you have a continuous current here, and then the bulk flow has to go in the opposite direction, which means basically you get this type of pattern. Yeah. So, and the transition really happens basically when this gap reaches the typical size. So this is a spin basically correlation function. So if it's negative, you're in such a state. If it's positive, you're in such a state. Good. So this just serves as motivation for basically building the type of models we're looking into. So what I would like to talk now about is really the equation I would like to focus on for the rest of the presentation. And there has been basically over the last 2 decades, we see a lot of progress in the description of active fluids, thanks to Jiram Ramaswamy and Mike Shelley, Christina Marchetti, and Julia Jürgens, and many others. And if you want to describe these active suspensions, typically what you need are coupled system of PDEs. So if you want to have an accurate model. So what you need is, say, a velocity field for the background solvent. So then you would need, in most cases, you can neglect the density variation. In some cases, you can't. So, but you have a velocity field, if you neglect this one, then you also need a concentration field for your active substance, and you need an order parameter field for whatever your object is. If it's polar, you have an additional vector field. If it's a nematic, you have an additional matrix field. So you get a very complicated set of coupled equations, and then you can study that and basically do linear stability analysis and so on. Now, what we wanted to do is basically trying to get something that's a little bit simpler. And
sorry. Before you get into the equations, could I ask you a quick question?
Yep, definitely.
Is there always only one backflow?
What do you mean by one backflow?
So there's a counterflow that goes in opposite direction than the flow at the edge. So always only one, or are there multiple zonal flows?
No. In that case, there's one. In that case, there's one. Yeah. So what you did in these experiments, obviously, we tuned the confinement to this magic 50 microns. If you look at the velocity profile, so you see there's basically at 0 at the center, so it's the speed, and it's basically positive, say, for the tangential velocity, and then it becomes negative at the boundary, which gives you like exactly 2 layers in a way. You have one zone that goes one way at the boundary and a bulk flow that goes in the opposite direction.
Right, but initially it didn't exist, right?
No, that's spontaneous. So you just fill it in and it forms spontaneously.
Is it trying to conserve like vorticity or angular momentum?
No, I don't think so. I mean, it's a highly dissipative system. So it's purely a fact basically of that the cells align at the boundary and they have these little propellers at the back and they push the fluid out towards the back, and then that creates a collective flow. And then the next row basically feels that flow and is advected backwards, and at the same time try to swim in this direction. But what you get is, for example, that the backflow is much stronger at the boundary because there you have essentially dipoles because these cells, monopoles because these cells interact with the boundary. So you have basically Stokes-lets that decay like 1 over R roughly, neglecting boundary. So that's stronger than a dipole that an individual bacterium has. So there's a very strong backflow just from the boundary, but you get just one layer. Okay. Okay, so just coming to these equations now, and so how active fluids are usually described, back to work that Jiram has done. So you can start with Navier-Stokes, for example. So in some cases you can neglect here the left-hand side. For us it will be essential to keep it. And what you usually do is you have a stress tensor that has 2 contributions. So it has the normal Navier-Stokes part, which gives you your viscous friction, and then you have an active part, which is somehow a function of these order parameters that you have. And typically you will have additional partial differential equations that govern the dynamics of these guys. So what we want to do is we want to have an equation that basically gives us flow pattern of this type, but has only a V field. Just one. And the reason that we want that is that we want to try to do something analytically. And so the way you can get that is basically by introducing a minimal extension of Navier-Stokes. And the basic idea is that if you look at Navier-Stokes and it's a dispersion relation, then it's essentially minus k squared, so all modes are damped. Now, what we know from pattern formation theory, for example, from Rayleigh-Bénard convection or so, that a very generic way of creating patterns is to change the dispersion relation. Yeah, so what we do is we just introduce a band of unstable mode in Fourier space. So that's a minimal thing that you can do. So the model is then minimal in the following sense. So everything that, so if you, maybe what I should say, if we go back basically, or we postulate this type of polynomial dispersion relation, that's mostly what I focus on, then you need a certain number of terms, and if you impose isotropy, basically you end up basically with 2 additional parameters here that you need. So this is a minimum that you can do. So because what you want is you want to have dissipation here at large wavelengths and small wavelengths. you want a finite unstable region, but then basically if you put this into this model, so there isn't anything that would damp or distribute energy from modes, between modes, so what you need is also this nonlinearity, and this is something we don't touch. So really, in that sense, we couldn't take anything out, so either the model would become boring or it would become ill-defined, yeah?
Just a small question. When I look at this equation, you describe it as the equation for the velocity field.
Yeah.
But presumably, dv over dt plus v dot grad v doesn't really have a factor of density in front of it. It's not true inertia, right? It's perhaps better thought of as the equation for the orientation, the polar orientation vector.
No, in that case, so when we think about this type of thing, I would really think about velocity and coupling stress, because
velocity, all right, but is that term inertia? Is there really a factor of density on the left-hand side as well?
Yeah, I mean, you could have a factor of density everywhere if you
Not
wanted
everywhere, but that wouldn't happen in Navier-Stokes. In Navier-Stokes,
to. Yeah, no.
U dot grad u has a density and the rest of it doesn't. So, if I
Yeah, I mean, what you assume here is anyway that we have incompressible fields. So
it's not that's not what I mean, really.
He's asking for interpretation.
Yeah, I'm talking. It's not actually inertia qua inertia. It's more like an equation of the polar order parameter after you eliminate the velocity.
Yeah, I mean,
probably, right?
If this how you want to see it. So because really the way I see it is, basically we have a vectorial order parameter in the end. We have an advective nonlinearity from that point of, and we have a linear instability. And what I would like to understand from now on really is just what does the combination of these two basic effects give us? And the reason, so if I plug these equations in, basically I get this type of higher order equation. And what it really allows us to explore is what happens at the interface of turbulence and pattern formation. So what you see on the left-hand side is really Banach convection. Yeah. So which essentially has these type of terms. So what's Swift-Horn? No, yeah. No, so what I can tell you is the following. I'll show that a little bit later. So you can take that as an effective equation for the velocity field that you would measure if you put tracer particles in, or the PIV field. And then if you assume that this is kind of proportional to the polar order parameter, then where you are, yeah. But at this basically stage, I would really think of that as an basically minimal extension of something that has a Navier-Stokes type nonlinearity and a linear pattern formation term. And we are interested what happens when these things kind of balance, when they're at the same scale. Yeah? So that's the idea. And this goes back to something that has been started in various contexts early on. So this is Vladimir Arnold. And basically not for the full PDE system, but when you look, so what he was interested in was reduced dynamics, and I will come back to these type of equations again. So what you can see here is essentially a simplified description of this type dynamics in terms of the triads. And so you can think about this term as a time derivative of representing time derivatives. This is your advective nonlinearity. Here in Navier-Stokes, that would correspond essentially to viscous damping, and then you typically need external forcing. So this is what is known as the Kolmogorov triad system. So there's another interesting case, basically, where you don't have this, but you actually allow this B to become negative. So you force through the linear term. So everything else being equal, so it's kind of the difference between having a linear growth or an exponential growth. So it's the net effect of these things. Now, yeah.
In your equation, the gammas are positive constants.
No, so two are positive, so they fix asymptotic behavior, and the one in the middle basically can be negative, and this gives us a double well shape. So, but again, so this is just a polynomial approximation of a more complicated dispersion relation. So you could always, what is important is really just the qualitative behavior. We actually check. So if you could take a Navier-Stokes type quadratic dispersion, and you put in just some peaks basically that become positive in a finite range in any form, you get qualitatively similar behaviors. Exactly. It's essentially what you need to get pattern formation in these systems. So that's the idea, basically. And Swift-Holmberg also for Rayleigh-Benard, so you make the diffusion term with the diffusion constant negative, and you need the next term to stabilize. Yeah, so, and this is the idea here too. Now, it turns out that if we look at the triads, and so do a little bit later, then well, maybe let me just come back. So what Arnold writes basically in his papers is so that the Lorentz type system is basically the one where you force here, and the Kolmogorov system is where you force here, and that this is fundamentally different. And also that the Lorentz system is much more sensitive than to initial conditions, and we will see that actually again. Now, it turns out, if you look at our equations, so essentially they're of the Lorentz type, more or less. Yeah, and this leads to interesting effects. Good. So now looking back, so I said we patted ourselves on the back. So we had this nice model, gave nice flow structure, and then we started digging, and then we found basically this paper by Berezhnev and Nikolaevsky. So they looked at the one-dimensional version of that. So they have additional terms here, but if you forget about these, then you have pretty much a 1D version of the model that I've been describing. So you have basically an advective nonlinearity and some pattern-forming terms in that case. So and the model has been studied, not by many people, but Tribelski and Suboy looked at it in the context of soft mode turbulence. So there's another example that I recently just basically became aware of, and this is in the context of lattice-Boltzmann codes. So Dan Rothman, who some of you may know here quite well, so he wrote a paper in 1989, so a long time ago, where he did something funny. So he said basically, let's change the viscosity rule in an LB code. So let's take a rule that maximizes the flux of momentum in the direction of the local momentum gradient. So it's basically anti-viscosity in a way. Good. Then he runs some simulations, so and he gets these type of flow fields. And this is again just the experimental figure. So the first experiment I'm aware of was John Kessler in '97. So I think then somehow several years earlier, he ran a simulation on bacterial turbulence, without thinking of bacteria in any form or so. But we should give him credit. So the field should give him credit for these things. Now, there's something else just for the active matter people here. So the last sentence of his abstract is that one reason he did that is so that he could reduce the viscosity in these LBM simulations. And I mean, this is exactly what there was a big hype about, this quasi-superfluidity or viscosity reduction, which is a nice effect. So he observed it there. So I don't know. I mean, I think one was really just to lower viscosities, but he found a lot of things basically. Good. Now coming back to our equations. So the really interesting things happen in 2D and 3D, and I hope I can convince you of that. So this is a nice minimal or toy model basically to study that connects to many of the things that we've heard about here in much more detailed description. So what I would like to show very briefly is that the model basically captures some essential aspects of experimental data, and it doesn't really matter so much what the system is, as long as there's some linear instability that generates flow patterns. So then the main benefit from our perspective is that you can find analytic solutions in various geometries, and that these analytic solutions actually, that you can see them in simulations. So they're not just basically some special cases, but they're basically survive, and they tell us something about the attractors of these equations. So then there's something that was unexpected. So these equations have more or less the symmetries of Navier-Stokes, except for basically that you select a certain K-mode where you see patterns. But if you combine this linear instability with this nonlinear advection, you get spontaneous chiral symmetry breaking. So this is something that we didn't expect at all. And then when we studied the system, so if you put all this to 0 here, you get the Euler equations back. So as an accident, more or less, so when we studied the triads, Jonas found basically a cubic invariant for the classical Euler triad. So even if this model is not useful for anything in the active matter context, so it gave us here a new invariant. So, but I think it's useful actually, but I'm biased. Good, so let me just briefly explain how we can fit these equations to data. And it's quite easy, it's mostly dimensional analysis. You have 3 coefficients available here. And so you can combine them into groups of certain dimensions. So for example, 2 of these essentially fix the most unstable mode. So that's kind of the typical vortex scale that you have in your system. So basically, that if you look at your system, you say, your vortex is 50 microns, or maybe it's larger, then this fixes one of these, basically in terms of the others. So you also get a typical vortex growth scale. So if you take the ratio, growth rate here, say it takes the value as a maximum. So if you divide these, you get a velocity. So that should be roughly the typical velocity that you see in your model. So that means you have 2 out of 3 fixed. So the one thing that you can play with is this width here. And this is the only key parameter that makes things interesting. So if you make that extremely wide, That means you pump in energy over a wide range of modes. So you're essentially back at Kolmogorov type behavior. So you find all the normal basically turbulent behaviors. If you make it narrow, then this really pattern formation competes with turbulent or advective energy transport, and this is where interesting things happen. So we will focus on the range where this is relatively narrow. Good. Now, just to show that you can capture some aspects, so if you take basically the data from, say, these bacterial experiments, so we can, with essentially that fitting method that I described, you get the velocity statistics, you get the correlation functions roughly right. You can take Swanimir data, basically. So the one thing that you have to do is you have to take data that is not in the nematic regime, because if you're in a nematic regime, you get elastic energy transfer and so on, so we don't want to be there. But you can also fit it, in principle. So it's possible, but it's not our main concern. So what's nice about the model is that essentially we still have Navier-Stokes. The only thing that we've changed is a linear operator on the right-hand side. So we can borrow all the techniques that have been developed by Keith Moffat or Fabian Valev and many others, and can really just basically repeat their analysis for these type of equations. And this is essentially what we did. So what I would like to basically describe how we can get solutions for the 2D case, and then we get them for the 3D case in essentially the same manner with a minor tweak. So in the 2D case, so if you take an infinite domain, we can go to the velocity stream function formulation, and this is what the equations look like. And then it's known for the Euler equation, so when everything here is 0, that you can find exact solutions by picking Fourier modes that make this term 0. So that you find exact stationary solution. So the only complication that we have, so we go to this class of solution, then we have to pick modes that also make the right-hand side 0. And then we have exact solutions. And there are many of those. So the only thing that you have to do is you have to pick modes that lie on the boundary of these, basically, of this unstable region. So they're essentially neutrally stable modes. So there are many of this type. So I've showed some lattices, lattice solutions here. So this is an Abrikosov lattice, so which is essentially a famous superfluid lattice. So and this just reflects the fact that you make the stresses here 0. Yeah. So the one thing I want to show is just a large-scale simulation. I don't have time basically to talk about in more detail, but why? So one reason why these equations are nice in a way is that you have a characteristic length scale available. So turbulence, to my understanding, is difficult because you don't have a length scale. So here you have something basically that fixes some scale in your system, and that actually allows you to understand also the mode statistics. So I'm not going to talk about something we currently writing up, but it's quite interesting. So essentially you get Bose-Einstein mode statistics in these systems. So good. So then now coming here to the connection to the Delos friends and also the Flatiron. So I don't know actually where this screen is here. So it may be some office here. So what I did is I just rotated the simulation. So this is now solving this equation on a sphere. Yeah, and so these are similar flow patterns to before. And later on, so what Rohit will talk about is when you start to rotate the sphere, because then you get new effects. So what I just want to explain already as a kind of an introduction for Rohit's talk is that you get exact solutions for a non-rotating sphere in the same form. So you take the equations, you can write them on a sphere, you change your dispersion relation a little bit because you get curvature effects. But in essence, what you can do now is you can look for expansions of, say, the stream function and spherical harmonics, and then you pick modes, basically, that make this right-hand side 0. So it's exactly the same procedure, just that you use spherical harmonics. Here's one example, basically, of such a stationary solution, which is exact. So now I want to show you in that example just that if I run a simulation, that I will find these type of solutions, basically. So this is now a simulation in time, so in a parameter. So this, now you have a state, transient state, that was exactly close to that, basically, eigenfunction in a way of this operator. So what the system actually does is the following, so in a rough sense. So you have all these exact solutions that are neutral modes, and the system more or less sits on one of these, and it pumps up energy, and then the nonlinearity kicks you to the next eigenstate. So we know a little bit about the attractors of these systems. Good. So now things become even more interesting in 3D. So you can do the same, or go through the same procedure as before. You can construct exact solution by finding Fourier, basically superposition that lie on these shells now in K-space, so on these neutral modes. So there's one subtlety that comes in, so you can construct your exact solutions basically in a way that you only pick modes that have a certain handedness. So they're either left-handed or right-handed. So I showed two solutions. So if you find a left-handed one, there's also a right-handed one. So here, basically vorticity, just one vorticity component of a 3D exact solution, and then basically you construct them from different modes, so you get different helicities. There's another nice thing about these exact solutions, so they are Beltrami fields. So which means that the vorticity and the velocity are aligned or anti-aligned. So this is basically your space of exact solutions. Now the question is again, do you see any of that in full simulations? So if we start a simulation with random initial conditions, then and we wait long enough, so then this is a stationary state in a way, or statistically stationary state. So and if we, what I plotted here again is the helicity at each point, and you see, so this basically in this simulation has settled onto a state where everything is positive. Yeah. You can also, and now if you run many of these simulations with different initial conditions, so small perturbations, so you 50% of the time you end up with a positive helicity branch on the positive helicity, 50% on the negative helicity branch. So that's surprising. So what it tells you is the linear instability and some advective nonlinearity give you this chiral symmetry breaking. And also the numerical solutions are close to Beltrami. So if you measure just the scalar products and plot them in a histogram, they're very close to Beltrami. So these have interesting attractors, so these type of equations. Now it's also interesting from a physics perspective. We have heard many things about it already, especially during the last discussion section. So I'm always a bit scared now to enter into that part. But so what, most of you are definitely on the geophysics side know is that if you look into 3D turbulence, so typically you have an energy cascade where you go energy flows from larger scales to smaller scales. And in 2D, so you also have basically an inverse cascade where you can have merging of structures. And that gives you basically energy transport from smaller to larger scale. So an inactive fluid is something we're quite interested in to understand this inverse energy transport, because this is how we function as humans in a way. So we have some energy activity input on small scales in cells, and then we do large scale coherent motions. So it's something we're kind of all interested in. Now, what Greichnan basically argued is that if you have isotropic 3D turbulence in an equilibrium system, so you shouldn't get this in 3D. Now, we have a non-equilibrium system, and we have spontaneous symmetry breaking. So we are not covered basically by his assumptions. And there was a very interesting paper by Luca Biferale a few years ago. So what they did is they just took Navier-Stokes, and then each step essentially they projected on a subspace of a given helicity and kept evolving the system. And then what they found is basically that there's an energy flux when a mirror symmetry is broken. So, and this is interesting because our model does that spontaneously. So you can ask, can you get some inverse transport in 3D in that model? So this is here the energy spectrum from a simulation that I showed before. So what we just did is we splitted the contribution that come from positive and negative helicity modes. So here, most of the energy sits in these positive helicity modes. So it's one of the simulation that lands on the upper branch. Now we can compute their fluxes, and then we see that there's indeed basically inverse transfer, inverse transport, which is of the order of 20–30% or so. So this dashed region here, so this is the range where you pump in energy. Good. Yeah, just as an aside, because there was some discussion about triads. So what we did is then we analyzed which triads contribute to this basically inverse transport, and the leading one is exactly the one that Fabian basically predicted for. And there are also others, basically secondary triads that transport energy. So good. Yeah. So now there's a question basically of whether we can actually understand analytically why this chiral symmetry breaking happens. And what you can do is really just follow up on Keys, Moffat's, and Fabian's work. So you basically look at the corresponding triad dynamics. So the basic idea of the triads is you look at a subclass of solutions that you can write in terms of a stream function and an extra field for the z velocity. You expand basically these two basically potentials in a way, or trial functions in terms of Fourier modes. And then basically if you look just at the leading order terms, you plug these in, so you get a system of ODEs, and you only keep the leading order nonlinearity. So, and you have basically these two fields, and in essence, so the first one is is independent. So the second one just couples to the first one, so we can only focus on this first equation. And this is more or less the equation that Arnold was looking at. So just to explain briefly how we come back to normal Euler equations. So this D matrix here has a dispersion relation on the diagonal. So this is 0 for Euler. So this is how you get back to the normal case. So everything that's special sits in this matrix. Okay, so this is just rewritten. Basically, the same dynamics was explicitly written for the first equation. And then basically you can show a couple of things. And the most interesting one is this one. So you can show exactly that for this type of system, the imaginary part of this basically triple product of the amplitudes decays, or basically can grow exponentially if there is a D matrix. But if the D matrix is not there, like for the Euler system, then this means this guy is a constant. So this is a new invariant. So there were two derived earlier for the Euler triads. So one basically by Kreichland, Lev, and Moffat. So they discussed those. And now there's a third one. And if you have a third one, you can characterize the phase space basically in that case, and you can actually show that the triadynamics basically lives on a 3 torus. So that's obviously a rigorous result that you can get. Good. So yeah, now coming back to these active triads to understand this symmetry breaking. So you analyze basically the triad system. So it's essentially a forced rigid body equation where basically everything is parametrized in terms of the modes. And then you find two qualitatively different behaviors. So one is basically you have unstable triads, the others you have stable triads. So stable triads land on a limit cycle, unstable triads grow. And we think this is essentially what happens. So if you start with a small perturbation, these unstable triads kick you up. And then basically eventually these stable triads will take over. And this is basically where your system sits later on. Good. So now basically I'm basically through. So this is what I already showed. So this is, and I would just want to transition out to Rohit's talk. This is what I showed. This is what you get if you simulate these equations on a non-rotating sphere. So if you switch on rotation, you get one extra term, and this extra term has a phi derivative where phi is basically the angle along the equator. So if you think about the exact solutions that we found, so if you want to have exact solutions, they cannot depend on phi. So in essence, these will be zonal jets. So if you run now, basically start to rotate the thing, you get these type of patterns. So you have some hurricanes here, and you have some zonal jets here. And the nice thing is, because everything is analytically tractable, so Rohit will discuss basically in his talk later that you can basically find basically complete analytic understanding, so and characterize the waves and dispersion relation and everything in detail. Good. So I would like to end here. So I hope I could convince you that this very simple toy model captures a lot of different systems. So it's not very accurate for a specific one, but it allows you to explore the interface between pattern formation and turbulence, and leads to interesting secondary phenomena like this chiral symmetry breaking. Okay.
So I think we have just about 2 minutes for questions, and I just wanted also, if you're on the Zoom and have a question, please speak up because we can't see you. But I'm going to go.
Yeah, hi. The experimental system you talked about initially is confined to a sort of layer on a substrate of something. There's a base, right? So there's a momentum sink.
Yeah.
The equations you look at are invariant under V going to V plus constant.
Yeah, exactly.
Does that matter? Because
it matters for something. For others, it doesn't matter too much. So what you can, so one thing I didn't talk about a lot is, so typically you would expect if you say look at these 2D patterns that the dominant wavelength that you see in your simulation is the one where you have the most unstable mode. But in 2D you get the advective nonlinearity transport energy to larger scales. So what you actually see after long enough time is a neutral mode, because then you're sitting close to a stationary solution. And this is also found if you make it a Toner 2 model, and you just create then patterns by making the diffusion term in Toner 2 negative, and then at the fourth order term.
So even with the polynomial term in the velocity, without any gradients, even if you include that, it doesn't change the story? Because in Toner 2, you're selecting
no, you need the pattern.
magnitude of V.
Yeah, no, you need the higher order derivative. You need the buckling term.
No, I'm saying the gradient independent terms. In Toner 2, you select a magnitude of the order parameter.
Yep.
And then in your variant, you will select a preferred wavelength
Yeah.
as well.
So, and if you do that in the Toner 2 model, these two things, you get very similar behavior to what we see here. I don't know about the chiral symmetry breaking, but that would be an artificial thing because, I mean, maybe it wouldn't if you think about it in terms of the polar order parameter field. Then it's okay. If you think about it in terms of velocity, it would be weird because then you would need a friction scale somewhere. But I think really, so fundamentally, I think what happens here is you have two effects competing. One is linear pattern formation, and you have an advective nonlinearity. And if you have these two things, you get behaviors that are quite similar. So, for example, what I mentioned briefly with the Bose field distribution. So you can look at totally different systems. You can look at a Faraday wave, so where you shake fluid. So if you go past the threshold where you have these lattice structures, so if you go to the chaotic state, so you can, if you look at the spectral properties of these two systems, they're very similar. I show you the spectra, you couldn't tell me which one is which. So I think there's something generic going on in the sense pattern formation with an advective nonlinearity gives interesting things. And it would be interesting to see if, these more complicated models or more accurate models that are discussed here, if you reduce them, and I think Jeff Wesel has tried it for magnetohydrodynamics actually, and you end up with things that look very similar to what we see for the toy model here.
Well, I hate to interrupt very interesting question and answer there, but I think we do it and move on. I don't want to get very behind, so thank you.
I want to thank the organizers. One of them is left, I think. All right, so it's my pleasure to be here. I want to tell something which I hope will be really of use to some of you here, and for those of you who do not use it in their work, some simple physics I hope to uncover in this talk. I'm going to speak about work which is done in collaboration with Mickey Mond from Ben Gurion University, Alexei Kritsuk, who is here, Petri Kapula from Göttingen, and Joshua Feinberg from Haifa University. So it's going to be about effects of supersonic turbulence, which are not have no parallel in incompressible fluids. So in astrophysics, we have the situation that often the Mach number of turbulence is large. So the large-scale eddies of turbulence are supersonic, and the ratio of RMS velocity to the speed of sound c is a large number. So we have another parameter in the system, and of course it can bring new qualitative and quantitative phenomena, and I'm going to discuss some of them. So what I'm going to concentrate is that density of gas, which is the fluid in this case, and concentration of dust, which I will speak of dust here as passive traces. I will not discuss the impact of equation of motion here, that they can have inertia and other effects can be there. So both of these distributions become singular, and they are supported on a multifractal set. And another phenomenon which I'll discuss is that, lines of magnetic field in the case where there is compressibility, after we divide magnetic field by density, the lines of this field are frozen in ideal flow. So compressibility apparently can have some effect on growth of magnetic field. So I'll speak of the effect of compressibility on small-scale magnetic dynamo. We'll start from the question, which is what causes multifractality and how we describe it. So, the knowledge that density is multifractal is quite common. What causes multifractality, I think, is not a common knowledge at all. So I'm going to speak of this, and this is this work which was published recently. So, fourth is here. I'll start from simple criterion, which seems to be less known. So it's observed that spectrum exponent of density sometimes is observed to be smaller than 1, sometimes it's larger than 1, in the sense that if you consider spectrum of density, it obeys some power law with exponent delta minus 1. Sometimes the exponent of decay, sometimes you have delta which is smaller than 0, and sometimes it's larger than 0. And here you can, some of this data was referred in Blakely's talk. There is a simple criterion when things get multifractal. Namely, if delta becomes positive, it's very easily seen that the integral over k diverges at large k. So we have that average second moment of density, which is given by that integral, diverges at small distances, which is the signature of multifractality. In real space, the spectrum of this law is very simple. It's this law, and you see that if delta is positive at small r, this diverges, and this exponent delta defines what is known as a correlation dimension of the attractor. So it's 3 minus delta, and the question is what regularizes the divergence at small r. So here comes the one of the defining properties of supersonic turbulence, which is the sonic scale. So, okay, I told you that at large scales, turbulent eddies are supersonic. However, velocity decreases with scale. So if you consider eddies of smaller scale, the velocity gets smaller. And at certain scale, you'll start having the velocity which is of the order of speed of sound. So that scale is called LC, sonic scale. Well, LS it must be. So you can define it in different ways. Okay, excuse me. So this is quite recent observation. It comes from this year. This work has not yet been published. However, this is open online. So this is observation of sonic scale. I must tell that there was no observation, clear observation of sonic scale before this work. And this is also, there are some dispute if this is the true observation. However, yes. Yes, this is a simulation. Please correct me if I use wrong terminology sometimes. So this is simulation. So you see here that you start with large, so on this axis you have the Mach number. Well, maybe I'll use the pointer. Okay, so on this scale you have Mach number. And here you have this distance in space, and this is structure function of turbulence. So you see that it changes the scaling at the point which corresponds to Mach number, which is 1. And the scaling goes to the Kolmogorov law. It is r to power 1 over 3. And here it's not r to power 1 over 3, it's roughly r to power 1/2. So you see clearly, or well, as clearly as you can see from this plot, that there is a change there, and it is a change in scaling, and this is because the turbulence below the sonic scale becomes, its velocity is already smaller than speed of sound, and effectively you have incompressible flow. So velocity spectrum changes from about -2 in the limit of infinite Mach numbers. It is widely believed and seems to be true that the spectra of velocity become k to -2, and at sonic scale it changes to k to -3. So the flow below the scale LC, the sonic scale, is incompressible. And this is telling you that density will not fluctuate below the scale, and this is what regularizes the divergence of density square at small scales. So what is the origin of multifractality? Here there is some step which we did, which is at the same time simple. However, it really lets you move from kind of dead end. So if you try to study directly the density, you need to study, well, it's turbulent problem, so at best you can hope to derive some very good scaling relation, which will reveal for you the multifractality of this field. And this is not so simple at all. It's not simple at all in the case of compressible turbulence. So instead, what we are telling is this. So, well, gas density designated here by rho obeys the continuity equation. Now let us consider a different field, which is concentration of dust, designated by n, which we, as I told, consider as passive traces, and it obeys the same continuity equation. So let's start from considering the passive field, both because dust concentration is of interest and because maybe we can learn something about the density. So, well, sometimes it's believed that these fields are in fact distributed identically. I'll speak of this later. So we consider some compressible turbulent flow V. We have a field N, which is passive. It does not react back on the flow. And we want to know the statistics of this field N. What can we tell about this? And whether it can be multifractal. So how can we approach this problem? Well, you can realize, if you think of this, that you want to have some scale invariance in the problem, because multifractality is associated with scaling. And for that, you need that solenoidal and potential components must scale in the same way, because if they scale differently, there is no possibility to create a multifractal distribution which is associated with scaling. So I'll tell more and more about this. So if you consider, then it is easily to understand the transition to multifractality. So if you have small Mach number, and of course you know very well the limit of small Mach number, in the leading order you have that velocity field is incompressible. It has the Kolmogorov scaling or with intermittent correction. And then there is a scaling of a compressible component, which is roughly known to be proportional to pressure spectrum, and it's K to -3. It's very different. There are other scenarios, however, in all cases, the scalings are very different. And then there's no multifractality at small Mach numbers. The density field is smooth. You increase the Mach number, then what happens is that the scalings of the components the gap between the scalings starts to close, and at certain Mach number, the differences of
number computed at larger scales or at smaller scales?
This is RMS large scales. So at certain Mach number, the gap closes, and the difference of scalings becomes really small. This was the data for Mach number about 6 can be found in Kritsuk work of 2007. Where I show you here the second order structure function. Vs is the solenoidal component of the flow, so it's the component which carries all the vorticity and has zero divergence. And Vp is, how does it work? Okay. Vp is the potential component which has zero curl and carries all the divergence. So we have similar scaling of these fields, and this tells quite simple things. So if you consider some blob of density, what happens with it? It starts to be stretched. Let's think simply. So there will be some dimensions which get decreased. Now, they get decreased because the distance changes. And then there is another degree of freedom. So this you can associate roughly with the whole flow, or let's associate it with solenoidal component for the sake of this argument. Then there is another change which happens with this blob, is change of density, which happens because of potential component. Now, you need to have that during the time that, say, the scale of the blob changes from initial scale L to L/2, the density must change also proportionally. And this is only possible if you have the same scaling of this component. So you need to have this self-similarity, and then you can create multifractal distribution. In contrast, if you don't have that, it's not possible. So this is the similarity of stretchings and compressions is the property which we need for multifractality. So I'll start describing this for what can be roughly called two particles cascade. So in the case of a pair correlation function of concentration, you have very simple interpretation for what the pair correlation function is. So this is the same thing, of course, as the spectrum of concentration. You can infer it from the property of two particles. It's a two-particle problem. You have two particles in compressible flow. You consider, say, a box with size which is integral scale of turbulence, or you consider larger system. It doesn't matter for this argument. Most of the time, the particles, of course, will be separated by the distance which is maximal of these two sizes, and occasionally they will approach. So you accumulate the probability that the particles are at some distance r, which is much smaller than L. This probability density function is known as RDF, radial distribution function, and it's measured quite a lot in other studies of particles. And if you think how the approach occurs, this occurs by the usual cascade type process that the particles are initially separated by the distance of the order of eddy of the integral scale. Then they approach randomly by a distance which is roughly L/2. Then this process repeats, and you get eventually that the particles get from scale to R to R. So there are a lot. This is a sequence of events where an eddy causes the particles to approach rather than, as usual, to diverge. So the particles start with scale L, they approach. Then they get to scale L/2. Eddy of the size L/2 again takes them and approaches them again. So they reach scale L/4. And this process continues until they reach the scale which is R, much smaller than L. And this process is completely consists of a sequence of independent steps so that you have the Markov property. Quite funnily, it really works here. So you can write this equation if you use timescale which is much larger than the timescale of eddies at the scale R which you're considering. Then you can do the next step. So you can write the Kolmogorov-Chapman equation. And for that, you have this general solution where L is some time-independent operator. And its kernel, so you have some evolution operator for the what's called sometimes propagator. Now, what do we know about this operator L? Not much. However, we can do the standard approximation, which is of the type which you use in Fokker-Planck equation, which in this case is known as Kraignard model, which most of you probably know. So we will model this operator L by the second-order differential operator, which allows us to derive a closed equation on the pair correlation function, which you could directly obtain from Kraignard model. Now, the model assumes that the flow of turbulence is Gaussian, zero mean, and is delta correlated in time. I want to make here a comment. Often people object Kraignard model. They tell it cannot be a good model of turbulence. Nobody tells it's a good model of turbulence. It's a good model of turbulent transport. It's good in the sense that it's qualitatively gives you a good result. So in this model, you can derive the pair correlation function. This result happens to be derived in our work with Grisha and Zhenya Balkovsky a long time ago. So in this case, you see immediately that if the scaling of compressible component, which is C, is the same as scaling of incompressible component, which is U, then you get the multi-scaling and multifractality. So I'll try to skip things. So you get the, you can describe all the fractal dimensions. You can reproduce these arguments. Then you can speak of gas density. It's an active field, and there is a very delicate question on the differences between these steady states of steady distribution of concentration of dust and gas. And the difference can be because there is no uniqueness of invariant state. So both density of gas and density of concentration of particles, they are invariant distributions. They are of this continuity equation. However, there is no uniqueness, and they can be different because of fine interaction of gas density with the flow. So you can describe for isothermal turbulence, you can write, this is again a result which is not known, though it's known in other fields, that you can write down the formula for fractal dimensions of any order. Then you can speak of acceleration in formation of planetesimals, which happens because of this formation of multifractal density. There is a parametric increase, and it's known in other areas that it influences the rate of formation of structures. So I would think that it certainly is relevant for planetesimals and many maybe other structure formation processes in astrophysics. Then about magnetic field, I'll only tell you the result. The result is that compressibility, in fact, influences small-scale dynamo in a very simple way. If you consider small-scale dynamo, it's the dynamo which lives on the scale where stretching of magnetic field lines by turbulence has the same timescale as the resistive timescale because of resistivity. And this spatial scale is much smaller than sonic scale. So effectively, magnetic dynamo happens at the scales where the flow is incompressible. So the only thing which changes is that you need to use a different effective Reynolds number, which does know about Mach number. However, the physics is the same as incompressible small-scale dynamo. So let me go to conclusions. That was too fast. All right, so the transition to multifractality occurs because of simple physics that as Mach number is increased, the scalings of solenoidal and potential components of the flow start to be similar, and then you can have a self-similar cascade where mass increases proportionally to the distance as you follow evolution of the blob, and the scaling exponent is fluctuating, which is what multifractality is. Theory can be done, and the question of the difference between active fluid density and passive concentration of dust is still open. I have a way how it can be measured, so we can speak later. Growth of magnetic field is the same as in incompressible flow up to change of parameters, and we have some things which I wanted to comment on how growth rates depend on intermittency of turbulence and on compressible dynamo in 2D. So you know that in incompressible case there is no dynamo in 2D. In compressible case there is a delicate question there. Thank you.
I think we're going to have to move forward with the next talk, so I would encourage any of you who have questions to this session. No, sorry, I was wrong. We have
I have a comment on the spectral scaling that you showed at the very beginning. I use it's on. So in observations, we also see the transition from cohomograph scaling to 1/2, from large scales to small scales. So that is different from the simulation. So the point I want to make is that the reality can be more complicated. For example, if your isothermal condition breaks down, or when you do conditional sampling of the turbulence. And for the dynamo part, I'm not sure that the dynamo picture is different on scales larger than the sonic scale if you do the decomposition of your turbulence to compressive in solenoidal modes. But I mean, it's good to check it.
Okay. Thank you.
We have time for maybe one more question. Great, let's then get something in.
Okay, thank you so much, and thank you for the opportunity to have a talk here. So yeah, we talk about observations of turbulence in the heliosheath and in the local interstellar medium close to the boundary of our heliosphere, so close to the heliopause. Let me just thank my collaborator, my former supervisor, my actual supervisor, and Dr. Richardson, that is PI of the Voyager mission for the plasma part. So the outline of the talk is the following. We will just introduce the Voyager interstellar mission and then look at motivation objectives of this work. I will show a couple of pictures from numerical simulations from Professor Pogorello, and then we will see the data analysis, statistical and multi-scale analysis of turbulence in these regions. So here we have the Voyager, and just very recently, Voyager 1 and also Voyager 2 exited the heliosphere. The heliosphere is represented in this sketch. We have a termination shock, and before termination shock, a solar wind is supersonic. Then we have a shock, a subsonic flow in the region called heliosheath. This region is supposed to be more complex than expected time ago. In fact, we suppose there is a low latitude region that is supposed to be more turbulent, and it's called the sector heliosheath. It's the region that is interested by the heliospheric current sheet generated by the solar magnetic field and Parker spiral. The unipolar heliosheath is the green region that's supposed to be less turbulence, more unipolar-like. And there can be magnetic reconnections. There are papers that try to demonstrate that it can be numerical simulation close to the heliopause. There can be instabilities and of course a turbulence throughout all the solar wind. Only very recently, Voyager 2 crossed the heliopause. There were so this is a picture from these recent publications just last month on Nature issue on this topic. So Voyager 2 crossed the heliopause in 2018, and while Voyager 1 crossed it in 2012. So now we have direct observation of the local or very local interstellar medium from these two spacecraft. Actually, the Voyager 1 can only provide the magnetic fields and the high energy particle, while Voyager 2 also has the plasma instrument already working, even though the data are quite noisy. So the objective of our study is to use these data that are the only in situ measurements from this region to understand the properties of the fluctuations and of turbulence. The point is that there are numerical simulations, global numerical simulations, that we can see some examples here, that can reproduce the global features of the heliosphere pretty well, and that's remarkable. For instance, the heliotail or the instabilities at the heliopause, larger scale structures like these magnetic barriers that have been actually observed very recently from Voyager 2. but the resolution is such that we cannot catch turbulence from this simulation. And turbulence is very important because it can affect the width of the heliosheath and the dissipation of magnetic field and transport of energetic particles. So the only direct measurements are from the Voyager spacecraft, but the point is that these data are very noisy and there are data gaps in the data. So even doing the most simple statistics like a power spectrum or structure functions is tough. So we developed, we tasted and developed some techniques during my PhD to get reliable analysis, statistical analysis of these data. I mentioned in particularly the compressed sensing technique that comes from the telecommunication environment, and it works. It allows us to recover the power spectrum from gappy data, and here we have up to 90% of missing data from the velocity field and 70% from the magnetic field. So here is, this is a numerical simulations where I plotted over the Voyager trajectory. So we see that both spacecraft are traveling at a latitude very close to the boundary between the region where we have the heliospheric current sheet that is actually quite broken. We see ripples and kind of turbulent at larger scales, and the unipolar region. So it's difficult to understand, since we have only one-dimensional data. Is not easy to understand the three-dimensional features and discriminate between these two regions. So this is actually the data. Voyager 1 at left and Voyager 2 at right. Voyager 2 looks like more, turbulent with a high level of fluctuations, while Voyager 1 samples magnetic fields from quite unipolar regions during the period when it was in the inner heliosheath. Here, the black line is the crossing of the heliopause, and I still don't have the data for the crossing at Voyager 2. We know that they knew the power spectrum at scales larger than 1 day, and we have this 1/f energy injection range, but the description at the smaller scales was actually missing. So that's what we did and published, and what we will see today. So just some formulas we have the magnetic field data, so we have to define some proxies for compressibility. Compressibility is one of the main features of turbulence in this region. We can define the intensity of turbulent fluctuation, anisotropy, so vector variance anisotropy. And typically with spacecraft data, we use the Taylor hypothesis, the frozen flow hypothesis, if the flow is much faster than the spacecraft, in order to convert frequencies observed into wave numbers. And sometimes this can be, this is not applicable, especially in this case at Voyager 1, when velocity of the flow is very small. So this is how the spectrum looks like in this region. We have this 6 decades power spectrum. We have a noisy band due to the magnetometer sensitivity. We observe a -1 range. Here is we are further into very close to the heliopause, so this range is reduced. It reduces with distance as we approach the heliopause. We have what we define inertial cascade range of the turbulent fluctuation, and then we have a second part of the inertial cascade range with a different slope that approaches -2, and especially for a parallel component, the compressive component of magnetic fluctuations. And then in the noise band, we cannot say much, but still we get some differences in the anisotropy. So maybe in the future we could do something here to understand what happens. Here is where the transition from magnetic hydrodynamic to kinetic regime should occur, because here is where we have the ion cyclotron frequency of the thermal plasma. The black line here represents the compressibility proxy. It's interesting that we see that there is this second typical scale in the system where we have a maximum of compressibility, and we also have, so this is for Voyager 1, the same. We have one spectral break, more evident, and -2, 2.5 slope, mainly due to the parallel component of magnetic field fluctuations, parallel to the mean field. Also, in this case, we have a very large values of fluctuations and compressibility that occurs at this scale, and then it decreases. We don't have an explanation yet for this, but in the system, we don't only have the thermal plasma, but we have pickup ions, energetic particles that are very important. They retain up to 80–90% of the energy of the system, and they can have larger cyclotron radiuses. So maybe this is what we are observing here is a pickup ion mediated turbulence, but that's only an hypothesis. To define the inertial range and the energy injection range, we also looked at higher order statistics, so power structure functions. Here we can see well that we have a break in these power laws here. The yellow line is the sun periodicity. The green line is a time or length scale related to the causality condition. In fact, we have to consider that only fluctuations detected at the spacecraft that experienced at least one eddy turnover or few eddy turnovers can be considered part of an active cascades. So a causality condition and age of turbulence is one of the factors that we use to understand why we do observe a spectral break here at this scale that is, I mean, it's smaller, quite smaller than the outer scale of the system, that in this case is 30 astronomical unit, the inner helioshift. And then second typical scale, and another change of the power law. Kurtosis, we look at intermittency, we expect intermittency in a turbulent field, and we see that we have a kind of power law in a growing intermittency and a maximum at this scale. And this was also found in the solar wind upstream determination shock in some conditions. It's also interesting to see if that we trace the structure function of order P against the third one. We have a pretty nice scaling, even though from the previous plot we see a lot of variation in this power law. And this is how we computed the relative exponents of the structure function, and this was based on a extended self-similarity principle discovered by Benzi in the 90s. We also tried to compute kind of energy cascade rate, magnetic energy cascade rate. I reported here just some formulas based on the Karman-Hoover relationship for magnetohydrodynamics, isotropic, incompressible, homogeneous, and so this holds in this condition for magnetohydrodynamic. We don't have velocity data, so we cannot compute the true energy flux, but we computed the flux only for the magnetic part that at least can give us an order of magnitude of such flux. And we also used some spectral-based formulas, and that's what we get. So we see that we have this level of energy flux and constancy through the inertial range. And at this scale also we see some variation. And it's also interesting to see that if you use the signed statistics, the noise somehow cancel out, while of course when you use the power spectrum we have wrong values. The interstellar medium, so beyond heliopause, this is the data of magnetic field, and compressibility based on this magnetic proxy and anisotropy and intensity. So we see that the flow, the interstellar, very local interstellar medium contains shocks and is affected by the sun dynamics because we have periodicity of 30 or 60 days and this larger scale variation of intensity and directionality of the fluctuations. It has been theorized that waves in the form of slow magnetosonic wave can be transmitted from inside the magnetopause to the interstellar medium in the form of fast magnetosonic waves that could be an explanation why we see this strong compressible component in the interstellar medium. But actually, we expected this fluctuation to decay with time, while this seems not to be true. We repeated statistics. Also in the interstellar medium, we see power spectra with the Kolmogorov light scaling. But what we see is that, intermittency doesn't hold at all scales, but start at the scale around 10 to the minus 6 hertz. So we don't know yet if this is what we observe is actually pristine interstellar turbulence or modified mediated interstellar turbulence from the heliopause. And I think that the second hypothesis is more likely. Just one more thing: the cascade of saturates when the intensity reaches the unit values. If you consider a field with a background flow, the maximum amplitude of the fluctuation can be double times the fluctuation, actually, so 180 degrees of rotation, and this gives an upper limit for the turbulent cascade. So this fit pretty well the change of slope we observe at Voyager 2, but not at Voyager 1. So maybe at Voyager 1, what we are looking is different kind of turbulence, more weak turbulence, more wavy turbulence can be. Okay, so I just leave the conclusion slides, and thank you for your attention.
A very detailed analysis of the spectrum. Did you look at the current sheets, which give you certain, say, reversal of the magnitude fields, resonance fluctuations?
How did I derive? You said.
I meant do you look at the structure of the fluctuation, not just the statistical one, but more.
Well, here I just look at the statistics of this one-dimensional data, because we have data from the spacecraft, and I don't have three directions actually. So what we can do is just look at one direction, and but we can make some assumption based on the direction of the velocity. We have for Voyager 2, if we go back to the spec, like this one. Okay, this L is supposed to be the direction. So if this is the velocity, is around, it's 10 times the velocity of the spacecraft. So under the Taylor approximation, if we consider spacecraft invested by the flow, magnetic field and speed are orthogonal. So this is a kind of radial direction, while magnetic field is in the other direction. It can be, in fact, for Voyager 1, we didn't put the length scale here because Voyager 1 is pretty slow, but also the flow is pretty slow. So maybe what we are observing here is maybe like fast waves in the direction of a magnetic field, or like Alphen waves at around 50 kilometers per second. Can be, but the numerical simulation will help us to interpret these results,
yeah,
at least at the larger scales.
Maybe I can talk to you more during the break.
Sure.
Yeah, thank you.
Great. We have time for one more very question.
So how you define the parallel and perpendicular magnetic fields?
So, well, this is based on the direction of the mean field. So just parallel or orthogonal to the direction of the mean magnetic field. that's we can compute the direction from the data. And for example, here we did 6 months running averages, and that was our main field here, and the fluctuation you see here are computed about these 6 months running averages. But we don't have the vector wave number. The vector wave number we have, provided the Taylor hypothesis works, is in the perpendicular direction. So I cannot tell you how the parallel spectrum looks like.
Great. Well, I'm going to propose we continue this discussion over coffee. Let's go again.
Thanks.